Hello friends, my name is Dr. Lalit Mohan Beri and you are watching Dr. Lalit's Academy. Dr. Lalit's Academy is a place where you find from class 6 to class 12 all subjects chapter-wise explanation. Ohm's law is a very important, a very favorite choice of examiners. So this is also an important topic as per your exam point of view. So to understand Ohm's law, first we do an activity. In this activity, we make an electric circuit and then we increase the current by putting an extra cell. We will increase the number of cells, see the amount of current flowing and the amount of potential difference across the resistance, which is a nichrome wire. Let's see what happened when there is only one battery. Say for example here, when the current through the nichrome wire passing was 0.1 ampere and the potential difference across the nichrome wire was 0.22 volt. When we increase the number of cell by one more, so the total number of cell was 2, the current was doubled, it is 0.2 now, and the potential difference across the wire is, how do we make this diagram? We keep on increasing the number of cells, then we measure the amount of current flowing through the nichrome wire and the potential difference across the nichrome wire. When the number of cells were 2, the current passing was 0.2 and the potential difference was 0.46. When the number of cells were 3, the current passing was 0.8. See, we just need to put a perpendicular line here and here, and we see that the potential difference across the nichrome wire was 0.8. When the number of cells were 4, the current passing through the nichrome wire was 0.4 ampere and the potential difference across the nichrome wire was about 1. If we see the ratio of potential difference across the nichrome wire and the current passing through it, no matter how much we increase the current by increasing the number of batteries, the ratio of potential difference and the current flowing was almost same. It was of the order of 2.3, 2.4. So this is the basic of Ohm's law. So we saw in this activity that as we keep increasing the electric potential around a resistance by putting extra batteries, the current which flows through the resistance, which flows through the circuit also increases. So we saw that the current flowing through a resistance is directly proportional to the electric potential applied around the ends of the resistance. Ohm's law says that the electric current flowing through a metallic wire is directly proportional to the potential difference. If the potential difference will increase, the electric current will increase. When the electric current is increasing, there will be more potential difference across the metallic wire. Across its ends, provided its temperature remains the same. The temperature is a factor which changes the resistance of a wire. So we saw that current is directly proportional to the potential difference across the wire, and the ratio of potential difference and current always remains a constant. We saw in this activity, no matter whether we increase how much we increase the number of batteries, how much we increase the current, ratio between the potential difference and current remains the same. The ratio of potential difference and current is called resistance and is denoted by R. So R is a constant for a given metallic wire. It depends on the metal which we use in that wire. So R is a constant for a given metallic wire at a given temperature and is called its resistance. The unit of resistance in SI unit is ohm and represented by Greek letter omega. This is called Greek letter omega. Okay, so this is the Ohm's law. So my friends, to understand the concept of resistance, I want you to listen to an example first. Forget about electricity, forget about resistance, just pay attention to this example. Say for example, you are about 20-30 guys, 20-30 boys and girls. They are walking through a path and the path is very narrow. Say for example, only 2-3 people can go through it at a time. Now, you tell me, when will you feel ease in walking? When the path is narrow or when the path is broad? Yes, you will feel easy or the resistance will be less when the path is broad. Okay, so when it will be difficult to travel the distance? When the distance is short or when the distance is long? Yes, you will feel more difficult to walk a longer path. So the resistance, so the work done by you will be more if the path is longer. So we can take two interpretations by this example. Like walking on a path will be easier if the path is broad, and walking through the path will be easier if the path is short in distance. In the same way, you guys are like electrons, and the metallic wire is that path. So electrons will feel more better, will feel more easy to travel if the cross section of the wire, is more, and electrons will feel more easy if the travel distance is less. So resistance is directly proportional to length of the wire and inversely proportional to the cross section of the wire. The thicker the wire, the lesser the resistance. The longer the wire, the more the resistance. I hope this example has made the concept of resistance clear to you. As we are familiar with the concept of resistance now, let's do the activity 12.2. In this activity, we have to take a nichrome wire, a torch bulb, a 10-watt bulb, and an ammeter, a plug key, and some connecting wires. This is all the component of circuit. Set up the circuit by connecting 4 dry cells of 1.5 volt each in series with the ammeter having a gap XY. Why we are having a gap XY? So that we can place different objects in between these XY terminals of the circuits. First we complete the circuit by connecting the nichrome wire in the gap XY. Plug in the key and note down the reading in the ammeter. There will be some current flowing with the nichrome wire completing the circuit by connecting X and Y. What is peculiar between nichrome wire? That nichrome wire is an alloy and is a good conductor. So there will be some reading. What we do next? Before that, why does it say always take out the key from the plug after measuring the current? Because if we keep the key inside the plug, the current will keep on flowing and that will decrease the power of our battery. Our battery will burn out early. So replace the nichrome wire with the torch bulb. Now we replaced XY with torch bulb. Now the torch bulb will, when we will close the circuit, the current will flow and the torch bulb will light up. Next, he wants us to place the 10-watt bulb. One thing which we should note here, that torch bulb is a very low power bulb. It must be less than 10 watt. We need to place the 10-watt bulb into XY. Now we will measure the ammeter reading again. What is the interpretation? The interpretation of the activity is that when we place nichrome wire, which is a good conductor of electricity, the current will flow. There will be less resistance, so there will be more current will flow. When we place torch bulb in between XY, the flowing current will be less. When we will place 10-watt bulb, the amount of current which is flowing will be much lesser because of the resistance offered by different material. So the gist of the activity is that to make you understand that the different material component offer different resistance. The concept of resistance, as you know, is to resist the flow of current. So more the resistance, the less current will flow through it. As we know the concept of resistance quite well now by the example of people walking on the path, when the path is broad, the walking on the path will be easier. When the path is shorter, less in distance, the walking will be easier. We will understand the same. We will apply the same principle in this activity. In this activity, we have a circuit and we will place different objects in different shape to complete the circuit. In first, he wants us to complete an electric circuit consisting of a cell, ammeter, to note the current flowing into the circuit in different situations. In first, we have to notice the current going through the nichrome wire. We will have some reading. Say, for example, we have a reading X. Replace the nichrome wire by another nichrome wire of same thickness but twice the length. What he is saying that in case number 2, thickness of the breadth of path is same but the length is doubled. Now electron have to move the double length, so the resistance offered is 2 times more. So the ammeter reading will be less. There will be less current flow because the cross section of wire is same but the length is doubled, so the resistance will be doubled and the meter reading will be X by 2. Now replace the wire with thicker nichrome wire. In situation 3, we have of the same length L. The length is as in the situation 1. A thicker wire has a larger cross section area. Again, note down the current through the circuit. You can think by yourself. Now that the cross section is more, so the electron have to face less resistance in traveling through the wire. If the cross section is double, he says thicker. Let's say the cross section is double. If the cross section is double, the resistance will be half. So the current flowing through this circuit now is 2x, 2 times the situation number 1. The next he wants us, instead of taking nichrome wire, connect the copper wire. This copper wire, situation 4 is copper wire. Let the wire be same length and same cross section area as the first wire. Note the value of current. This is the most important part which we need to understand. This is also relevant to our day-to-day practical life. I will just explain this. Now in situation 4, we have a copper wire with same thickness and same length. Now what will be the ammeter reading? Copper is a very good conductor of electricity because the resistance offered to electrons movement is less. So the resistance is less. It's a good conductor. So the ammeter reading will be more than the nichrome wire in situation 1 because copper is a good conductor. So we saw that in situation 1 there was some of resistance. In situation 2 the resistance was doubled in situation because the length was doubled. In situation 3 thickness was doubled, so the resistance was half. In 4 the metal, the component of wire was changed. It was copper in place of nichrome, so resistance was less. Now see the practical implication of this experiment. While you do the wiring in your house, while you make a electric circuit, whenever you go to market to purchase wire, you always see that the wire should be made up of copper, The wire should be thick. The thicker wire is always better. It offers less resistance. Thin wire offer more resistance. You must have seen that when you want to run some instrument which electric instrument which needs more power, more electric current, like your heater, like your electric iron, you want a thicker copper wire. So why we take copper? Because number one, copper offers less resistance, so the flow of current is more. Why we take thicker wire? Because the cross section of wire, more broad, more bigger, more thicker the wire, less resistance. And we take the required length of wire only, because if we take the more length wire, the resistance will be more. Let's formulate the resistance of a conductor in equation. Now in the previous activity, it is almost clear, it is completely clear that the resistance of a conductor depends on its length. The more long, the lengthier the conductor, the more the resistance. It is inversely proportional to the cross section. That means the thicker the wire, the lesser the resistance. The thinner the wire, the more the resistance. And also it depends on the nature of material. So it depends, is directly proportional to length, inversely proportional to cross section, and also the material by which the conductor is made. So resistance of a conductor is directly proportional to L over A, length over cross section area. To remove the sign of proportion, we need a constant of proportionality. It is called rho. Rho is the constant of proportionality. Rho depends on the constituent of the conductor. Lesser the value of rho, more better the conductor is. So this equation is very important to calculate the resistance of conductor. Resistance is equal to rho L over A. Now this is an exhaustive list of electric resistivity of material. Lesser the value of electrical resistivity, rho, the more better the conductor it is. So we see that value of rho for copper is less than iron. So the interpretation is that copper is a better conductor of electricity. Silver is further better conductor of electricity. Gold is even better conductor than silver. Practically, the wires are made up of copper, aluminium and iron. The wire which we usually use in our household to transfer electricity is made up of copper, aluminium and iron. Out of these three usually used wires, copper is the best conductor of electricity. So whenever we purchase a wire from market, we make sure that whether the wire is made up of copper and how thicker the wire is. So if the wire will be thicker, it will have less resistance, it will be a good conductor. If the wire is made up of copper, the rho value is less, so it's a good conductor. Let's do the exercise. So on what factors does the resistance of a conductor depends? We know this in detail. The resistance of a conductor depends on, I told you earlier to remember this equation, resistance R is equal to rho length over cross section area. So the resistance of a conductor depends on length of the conductor, the cross section area of the conductor or the wire, the material used in the conductor. Yes, and another important thing is temperature of the conductor. All the value of rho given in that list were at standard temperature 20 degrees Celsius. If the temperature varies, the atomic structure inside the wire also changes, and the resistance of the wire, resistance of the metal also changes. Next question is, will current flow more easily through a thick wire or a thin wire? You just need to recall the example I gave you. If the path is narrow, it will be difficult for more people to walk on that path, and if the path is wider, it's easy for people to walk on the path. The current will flow more easily in a thick wire. And to explain this, we can give the equation also. R is equal to rho L over A is the cross section area. Resistance is inversely proportional to the cross section area of the conductor. So we can say the thicker the wire, the lesser the resistance. Question number 3. Let the resistance of an electrical component remain constant while the potential difference across the two ends of the component decreases to half of the former value. What changes will occur in the current through it? Resistance same, and the voltage, the potential difference across the wire is reduced to half. What will happen to the current? So we know by the according to Ohm's law, voltage V is equal to I over R, or current I is equal to V by R. The potential difference, new potential difference V dot is half of the initial potential difference, that is V dot is equal to V by 2. The new current I dot is equal to V dot over R. As we know, V dot is V by 2, so it becomes I by 2. Therefore, the amount of current, if we decrease the potential difference to half, the current will also decrease to half of the first value. Question number 4 is, why are a coil of electric toasters and electric irons made up of an alloy rather than a pure metal? This is a very important question in the practical, has a practical implications. See, what do we want in electric coil and electric wire? When we want to generate more heat, we take material which has more resistance. The more resistance, the more heat will be generated. And when we want less heat to be generated, we take the wires made up of material with less resistance. Why the coil of a heater is made up of alloy? Because alloy has higher resistivity, is alloy usually higher, because when they will heat up, pure metal will melt down, but the alloy which has usually have higher melting temperature will not easily melt. Hence the coil of a heating appliances such as electric toaster and electric iron are made up of alloy rather than pure metal. Now the last question is, use the data on table, that table which gives resistivity of material, and which among iron and mercury is a better conductor. The lesser the rho, the good conductor. So the iron's resistivity constant is lesser, so iron is a good conductor. Which material is the best conductor? Resistivity to iron is less than mercury, so iron is a better conductor. According to that table, all the material listed in that table, silver has the lowest resistivity constant, so is the best conductor. And you should also know that gold is even better conductor than silver. So why don't we make all the wires in our house from silver or gold? Yes, because silver and gold are very costly, but for knowledge one could remember that the gold is the best conductor, followed by silver, followed by copper, followed by other materials. Now we are going to study resistance of a system of resistors. Now we know in a fair detail about the resistance. What are the factors which determines the resistance of a conductor? What if we joint resistance into different combinations? So what will be the resultant resistance of the system? Now we will study this property. The different resistors can be joined in two ways. The number one is series pattern. The word series signifies one after another. Here we see first there is R1 resistor, then at the end of it R2 is joined, and at the end of it R3 is joined. So this combination of resistance is called resistors in series. The other combination could be the resistors in parallel. Here we see that potential difference across the battery is equivalent to potential difference across each wire, or the resistors are side by side. So this combination of resistors is called parallel combination of resistors. Now let's see the resultant resistance of a combination of resistors in series pattern. In series pattern, we see that the current is coming through this wire. First it is going in R1, then it is going in R2, then it is going in R3. By the Ohm's law, we know that V is equal to IR. The potential difference across the resistance is equal to current flowing through the resistor into resistance of the resistor. In this combination, in three resistors, the common thing is current. The current going through all these resistors is same. So let the potential difference across R1 be V1, R2 be V2 and R3 be V3. By the Ohm's equation, IR, the voltage across these three, is the voltage across the battery, which is V. V is equal to I into R. R is the resultant final resistance of the combination of resistors. So IR is equal to I R1 into I R2 into I R3. Here the current is same. The variation is in voltage. The current is all the resistors is same. So the resultant, so if we put this equation into Ohm's law, IR become IR1 plus IR2 plus IR3. Current get cancelled, so we get the resultant RS. A resistance in series pattern is equal to R1 plus R2 plus R3. So the final resultant resistance will simply be added. You can also understand this simply by thinking that the electrons have to travel each resistance one by one. So electrons have to travel all the difficult resistors. So the resultant resistance in series pattern will be simply added. Now let's see what happens to the total resistance value when we connect the resistance in parallel pattern. In parallel pattern, resistors are joined side by side. Before getting the formula for combination of resistance in parallel, you can just think that if there was only one resistance, say for R2 in the circuit, the electrons have to travel only via this route. Okay, but now there are two alternate routes are open for traveling electrons. You can follow the example. If there is only one narrow path, you guys will travel through it. If you find another two paths, you will feel ease in going through the path. You have two alternative paths now, R1 and R3. So the resultant resistance will be lesser, much lesser than the individual resistors, because electrons have alternative paths to travel now. In the series pattern, we saw that the current was common going through all resistors, but in parallel pattern, which is common across all resistors, yes, it is the potential difference. The potential difference across all resistors is same, but the current is different. Current will divide into three portions. Say for example, the current going in resistance 1 is I1, and R2 is I2 and R3 is I3. So total current is equal to V over RP, which is the total resistance in parallel combination. So I1 is equal to V over R1, V will remain same, potential difference. I2 is equal to V over R2, I3 is equal to V over R3. Because I is same, so V over resultant resistance in parallel combination, V over Rp is equal to V over R1 plus V over R2 plus V over R3. So the final equation becomes the resistance in parallel combination 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. Now you may also get a combination of resistance both in series and parallel. Say for example, in this diagram you can see that R1 and R2 are joined in parallel combination, R3, 4, 5 are joined in also parallel combination. But what will be the resultant resistance of the circuit? Let's see. See, first we will calculate the resistance of individual system. Like we will calculate the resistance of R1 and R2 by adding them in parallel combination. Then we will add resistance of R3, 4, 5 by adding them in also in parallel combination. Now if you see properly that this assembly and this assembly is joined in series pattern. So the combination of R1 and R2 will be simply added into the combination, the final resistance of R3, 4. So when you have such complicated circuits of resistors, first find the resistance of individual component and then add them all together. Now let's do the exercise. Now the question number 1 is, just the equivalent resistance from the following when the following are connected in parallel: 1 ohm and 10 to the power 6 ohm, 1 ohm and 10 to the power 3 and 10 to the power 6. First you need to understand that this 10 to the power 6 is 1 million ohm. So this is a very high resistance value, and this is a very low resistance. So this is a very good conductor, this is extremely bad, and this is somewhere in between. So again we can see the previous diagram. This we just say that question number first A part, if R1 we take R1 as 1 omega, R2 as 10 to the power 6. So if we add, they are in parallel combination. If we add 1 over R is equal to 1 over Rn plus 1 over R2. 1 over R1, R1 is 1 over 1 plus 1 over 1, 10 to the power 6, which comes almost to 1. So the resultant combination of the resistors will be 1 ohm, because R2 is almost non-conductor of electricity. So in system only R1 will be counted. In the B part of the question, he says, what if we joined R1 to 3, when R1 is 1 omega, R2 is 1000 and R3 is 1 million. In that case, the resultant combination is 1 over 1 plus 1 over 1000 plus 1 over 1 million, which comes about 0.999, which is also about 1 ohm. An electric lamp of 100 ohm, a toaster of 50 ohm and a water filter of resistance 500 ohm are connected in parallel. So when they are connected in parallel, the resultant resistance will be less to a 220 volt source. So what is the resistance of electric iron connected to the same source that take as much current as all three appliances, and what is the current through it? It's a very simple question, you just need to calculate it. First we will find by the Ohm's law that what is the current flowing through the combination of these appliances in parallel form. Then the electric iron is taking the same current and we know the voltage, so we will find the current, we will find the resistance of electric iron. See, the resistance of three appliances in parallel combination, final resistance is 1 over 100 plus 1 over 500, which become 60 over, so R is 500 over 60. So according to Ohm's law, we calculate the current, which comes out to be 7.04 ampere. Same amount of current is going through electric iron. So the resistance of iron is voltage over current, which is 31.25 ohm. The third question is, what are the advantages of connecting electric devices in parallel with the battery instead of connecting them in series? We have seen in the previous slides that when we connect the electric devices in parallel combination, number one, the voltage, the potential difference across the electric devices remains the same, and the final resistance also decreases. That's why we joined electric devices in parallel combination. You can see that if these are three appliances, the voltage difference will remain same across the appliances and the resultant resistance will also decrease. Next question is, how can three resistors of resistance 2, 3 and 6 be connected to give a total resistance of 4 ohm and 1 ohm? Now this is just a tricky question. You don't need to get confused with it. It's a sort of a mental ability question. So say, how can we make a combination of 4 ohm? We will join 6 ohm and 3 ohm in parallel combination, which will come 1 by R is equal to 1 by 3 plus 1 by 6, which will be 2. Then we will add it into 2 in series combination. So the resultant of parallel combination is 2. Then we will add in series combination, it will become 2 plus 2, 4 ohm. How can we get 1? We will add all of them in parallel combination. So 1 over R is equal to 1 over 2 plus 1 over 3 plus 1 over 6, which comes 1. Okay, the next question is, what is a highest and a lowest total resistance that can be secured by combination of 4, 8, 12 and 24? Highest when we will add in series combination, lowest when we will add in parallel combination. just a matter of calculation only. It will become highest R equal to 4 plus 8 plus 12 plus 24 will become 40H. Lowest resistance is equal to 2 ohm. Let's understand the heating effect of current. To better understand the heating effect of current, you just need to recall the basic structure of atom. The basic structure of atom has a nucleus in center and electrons orbiting around the nucleus in orbits. The electrons which are at the outermost orbit are free electrons in metals. The electrons whose orbital class is at a distance, the far distance from the nucleus. So the electrostatic force between the nucleus and those electrons are very less. So these electrons can skip the class and move around freely. So these are called free electrons. Now free electrons are responsible for conductivity. Now the heating effect of current can be understood very easily. Say for example, you understand there's a wire and we apply a potential difference between the two ends of wire, so the electrons will move in a direction opposite to the direction of electricity. When electron move freely, they do a sort of a Brownian motion. The electron collide with other nucleus, electron collide with other electrons. So this collision produce heat. More the number of electrons, more the number of collisions, and more the time for collision, the heat effect will keep on increasing. So a very good example of this heating effect of current is electric bulb. What happens in electric bulb, when the electricity flow through the filament, the electrons collide with each other and with nucleus and produce heat. The heat heats up the filament and the filament is heated up to a temperature where it glows and emits light. Now the same can be understood by seeing this diagram, that if we apply, as I already told you, if we apply a potential difference across the wire, the electrons will keep on moving, will collide with nucleus, which collide with one another and produce heat. Now consider the current I flowing through a resistor of resistance R. Let the potential difference across it be V. So let T be the time during which a charge Q flows across. So the work done in moving charge Q through the potential difference V is VQ. Okay, so work done is equal to VQ. So power is equal to the rate of work done, VQ over T. Therefore the source must supply energy VQ in time T. Hence the power input in the circuit by the source is VQ by T. So Q by T. So rate of flow of charge is I. So the power is equal to VI. So this is how this equation comes. This is a very important equation. Power is equal to VI. On the energy or the energy supplied to the circuit by the source in time T is, so total energy supply is power into time. So it will become so energy or heat, so P into T, which is VIT. So what happens to this energy expended in the source? This energy get dissipated in the resistor as heat. So this is the heating effect. The energy is converted into heat. So thus the steady current I and the amount of heat H produced in time T is H is equal to VIT. Heat energy is equal to power into time. Power is equal to V into I. And applying Ohm's law, V is equal to IR. So the equation become I square RT. So these three equations are very important. You should memorize it. You should never forget it. This will help you until you appear into your pre-medical, pre-engineering examination. So these three equations will give you a short answers. They are very and you will definitely get a question at the heating effect of electric current. So one should memorize P is equal to power is equal to VI, or total heat produced is equal to VIT, or heat, or H is equal to I square RT. Okay, now let's do the exercise. Why does the cord of an electric heater not glow while the heating element does? We have already done this question in a modified form earlier, because the heating element has more resistance, so the more heat is produced, so it heat it up and glow, but the cord has less resistance, it doesn't glow. So the heating element of heater is made up of alloy which has very high resistance. So when the current flows through the heating element, it becomes hot and glow, while the cord, which is usually made up of copper or aluminum or iron, has low resistance, so it does not glow. Now this is the heating element of the heater. So it is made up of alloy, so it has a high resistance, it glows but doesn't melt down. Now here there should be a wire which should be made up of copper, which has low resistance, which doesn't glow. Now see the next question. Compute the heat generated while transferring 96,000 coulombs of charge in 1 hour through a potential difference of 50 volt. It's a simple question. You just need to put the values into the equation. So heat generated is equal to VIT. So Q I is equal to rate of passage of charge, Q by T. So it becomes 96,000 by time. 1 hour is equal to 60 into 60, 3600 seconds. It becomes 80 by 3 ampere. So the total heat generated is equal to VIT. So which becomes 4.8 into 10 to the power 6 joule. It is not into 100, 10 to the power 6 joule. Next question. An electric iron of resistance 20 ohm takes a current of 5 ampere. Calculate the heat developed in. Again the same, you need to put the values in through the equation. So the heat generated is equal to I square RT. I is equal to 5 ampere. I square 5 into 5. Resistance is 10 and time is 30 seconds. It becomes 1.5 into 10 to the power 4 joule. Now let's see what is electric power. We know that power is the rate of doing work. Power is the rate of doing work is called power. This is also the rate of consumption of energy. So power is equal to, in the previous slides we saw power is equal to V into I, or we can put the Ohm's, by the Ohm's law it becomes I square R or V square over R. So SI unit of power is watt. It is the power consumed by the device that carries 1 ampere of current when operated at a potential difference of 1 volt. So 1 watt is equal to 1 volt into 1 ampere. So watt is, so another name of watt is volt ampere. Okay. The unit watt is very small. I need to say this, it is very small. Usually the amount of amount of power which we consume in our day-to-day life is much more, so we want a unit which is bigger. So therefore the actual practice we use a much larger unit called kilowatt. It is equal to 1000. Kilo stand for 1000, so kilowatt stand for 1000 watt. Since the electrical energy is the product of power and time, the unit of electrical energy is therefore watt hour. 1 watt hour or 1 kilowatt hour. 1 watt hour is the energy consumed when 1 watt of power is used for 1 hour. The commercial unit of electric energy is kilowatt hour, which you see in your electrical bills. It is 1 kilowatt hour. 1 kilowatt hour is 1000 watt into 1 hour, which is 60 into 60 seconds. So it becomes 3.6 into 10 to the power 6 joules. One should also remember this this value. 1 kilowatt hour is 3.6 into 10 to the power 6 joules. These are very important equations. These should be memorized as such. Now let's do the questions. So what determines the rate at which the energy is delivered by a current? The rate of consumption of electric energy in an electric appliance is called electric power. The rate of consumption is called electric power. Hence the rate at which energy is delivered by a current depends on the power of the appliance. Question number 2. An electric motor takes 5 ampere from 220 volt line. Determine the power of the motor and the energy consumed in 2 hours. You just need to put the values. Power P is equal to VI. So the power of the motor is 220 volt into 5 ampere, 1100 watt, and the energy consumed by the motor is power into time. Power is 1100 watt into time, which is 2 hour, 2 into 16 into 16, which become 7.92 into 10 to the power 6 joule. So friends, this is all about electricity. I hope you understood few concepts of electricity. Please give me your valuable feedback. You can email me at contactdrlalit@gmail.com, or you can simply write in the comment section. Thank you very much.